Hi, my name is Abigail Batten. I'm in heat and mass transfer with Professor Jimmy Lawrence, and today I'll be solving two heat and mass transfer problems using Python coding. The problem statement given said that we were given a brick wall with a thickness of 0.5 meters with one starting temperature on one surface at 600 degrees Kelvin and 425 Kelvin at the other. The goal was to find the time that it took in order for the center temperature to reach 425 Kelvin, and initially the entire wall was at 300 K. I used the equation shown in the middle in order to solve this problem in Python, and for part B, I was to plot the temperature change over time and determine the total time for the center temperature to reach 425 K. For part C, I was to find the stability criteria for a 2D and 3D system and be able to explain what they look like. For the second problem, I was able to select a one-dimensional problem from my textbook, which I used Chapter 3, Problem 31, and I built a code for that in Python and also did hand calculations in order to back my work up. For my first problem, I started by defining my variables. For my change in x across the wall, I used a value of 0.025 meters. For my change in time, I used a value of 360 seconds, which is equal to 0.1 hours. And I also calculated the value of a constant that I called K, which is equal to thermal diffusivity times the change in time divided by the change in x squared. For my second block, I wanted to ensure that the value of K was correct, so I printed it out to check it. And in my third block, I set up three arrays that were used later on in my calculations. For the starting temp array, this is equal to the starting temperature across the brick wall. For my second array, next temp, this is equal to the temperature across the brick wall at the following time interval. And my third array, called brick wall, showed the different values of x across the entire length of the brick. For my next block, I have a series of while loops that actually help me solve my problem. The first while loop runs until the center temperature reaches the target value of 425 degrees Kelvin. The second while loop calculates the temperature at the following time interval, and the equation shown in the line directly beneath that is the manipulated equation from the given homework statement. The third while loop sets up the starting temperatures equal to the temperatures that were just calculated. I also have a time counter variable that keeps track of the total time elapsed. The round time and next temp variables use rounding in order to round the time and center temperature to 2 decimal places. The two print statements print time and the center temperature of the brick wall for each respective time. The interpolated time variable, shown directly beneath that, is used to find the exact time when the center temperature equals 425 degrees Kelvin at the end of the problem. I also have a series of matplotlib statements shown beneath that, which plots the temperature in Kelvin versus the position across the brick wall in meters. And the last statement rounds the interpolated time value, which is the time when the center temperature equals 425 Kelvin, to 2 decimal places. My code ran for approximately 170 iterations, and the graph shown below is the last iteration that was conducted at a time of 16.8 hours and 425.1 degrees Kelvin. It shows the temperature in Kelvin at each position across the brick wall, and the statement at the bottom states that the center temperature of the brick wall is 425 degrees Kelvin when the time is equal to 16.78 hours. That was found using my interpolated variable, and I also have approximately 6 other graphs that show the change in temperature for each position across the brick wall for 6 different time values in my appendix. For part C of my first problem, I was asked to talk about the stability criteria in 2-dimension and 3-dimensional transient heat transfer. If you notice the equation at the top, this is the one given in the problem statement for 1 dimension. If you look on the far right, it shows the value for the stability criteria, which is less than or equal to 1/2. And this is because if you look at the term in parentheses, if you were to plug in the value of 1/2, the entire term would go to 0. If the value of the stability criteria or constant K were greater than 1/2, you would find negative values within the parentheses, which would cause the temperature to go down, which does not make sense in the context of this problem. I found the equation directly beneath for 2-dimensional heat transfer on the internet, which is shown by the blue block. There are two additional terms that were not shown in one-dimensional, which is the top and bottom values. And if you look on the far right, the stability criteria is that tau is less than or equal to 1/4, which is due to the term in parentheses in the equation, which has the same concept as the first problem, where if the value were greater than 1/4, you would end up with a negative term. From the two equations above, I was able to infer that for three-dimensional heat transfer, the equation would look like the one shown here. There are two additional values for the front and back in terms of temperature, and I assume that the stability criteria would be less than or equal to 1/6, which is shown here, with the same thing occurring if the value were greater than 1/6, having negative terms, which would cause the temperature to decrease, which would not make sense in the context of the problem. For my second problem, I was allowed to choose a problem from my textbook, so I chose Chapter 3, Problem 31. The goal was to determine the convective heat transfer coefficient necessary to thaw ice on a car windshield. In my first block, I defined my variables. In my second block, I calculated the heat flux through the windshield. And for my third block, I calculated the thermal resistance. And in my last block, I used the two values above in order to calculate the heat transfer coefficient. And what I found was that the convective heat transfer coefficient of warm air blowing over the inner surface of the windshield was equal to 112 watts per meter squared per Kelvin. Prior to running my code, I did hand calculations of the values in order to determine that I was on the correct path. As you can see, my first value is for my heat flux, which ended up being 2,000 watts per meter squared. I then calculated thermal resistance, which came out to a value of 0.0175 meters squared times Kelvin per watt. And then I found my heat transfer coefficient, which ended up being 112 watts per meter squared per Kelvin, which was equal to what I found using Python. My code generated around 170 iterations with graphs for each time iteration for my first problem. I included 6 graphs in the next 3 slides to illustrate the temperature profile change over time. Thanks for watching.